Imagine a region of space so vast, so impossibly empty, that if our entire galaxy were placed at its center, the nearest neighboring galaxy would be 10 times farther away than anything we can see in our cosmic neighborhood. A void so large that light takes 500 million years just to cross it. A silence so profound that it defies the very mathematics we use to describe the universe. In 2007, astronomers discovered something that shouldn't exist, a hole in the fabric of the cosmos, nearly 1 billion light-years across, the Eridanus supervoid. But this isn't a hole created by something being removed. This is a fundamental absence, a cosmic wound where the universe simply isn't. Within this void, there are approximately 10,000 times fewer galaxies than there should be. The cosmic microwave background, the afterglow of the Big Bang itself, bears a cold spot aligned with this emptiness, a temperature anomaly that violates our models of how the universe should have evolved. What if this void isn't an anomaly at all? What if it's evidence of something far stranger, a scar from before the Big Bang, a signature of parallel universes colliding, or a region where the fundamental constants of physics are slowly dying? Today, we journey through evidence that challenges everything we understand about cosmic structure, the Big Bang, and reality itself. Prepare yourselves. We begin. The discovery. In 2004, astronomers analyzing data from NASA's Wilkinson Microwave Anisotropy Probe noticed something disturbing in the cosmic microwave background radiation. This radiation, light from 380,000 years after the Big Bang, should be remarkably uniform, and it is, except for one region. In the constellation Eridanus, there exists a cold spot, an area of sky roughly 5 degrees across where the temperature of this ancient light is 70 microkelvins colder than the surrounding radiation. That might sound insignificant, 70 millionths of a degree, but in a map that shows the birth of the universe itself, this represents a profound anomaly. Dr. Lawrence Rudnick at the University of Minnesota decided to investigate. He cross-referenced this cold spot with radio survey data, looking at the distribution of galaxies in the same region of space. What he found was extraordinary. The cold spot aligned perfectly with a supervoid, a massive, underdense region of space between 6 and 10 billion light-years away from Earth. This wasn't just an empty patch of sky. This was a three-dimensional sphere of emptiness, spanning nearly 1 billion light-years across. To put that in perspective, if you could place one galaxy every million light-years throughout this entire volume, you would find approximately 10,000 fewer galaxies than expected. Think about that. 10,000 missing galaxies. The Eridanus supervoid, as it came to be known, represents the largest known structure, or rather, the largest known absence of structure in the observable universe. But cosmic voids themselves aren't unusual. The universe has a web-like structure, massive galaxy clusters connected by filaments with voids scattered throughout like bubbles in foam. These voids are common. What makes the Eridanus supervoid different is its size and its association with that cold spot in the cosmic microwave background. Here's the problem. According to our understanding of cosmology, a void, even one this large, shouldn't create a temperature anomaly this significant. The integrated Sachs-Wolf effect, the phenomenon by which photons lose energy passing through expanding voids, can account for perhaps 10 to 20 microkelvins of cooling, not 70. When Rudnick published his findings in 2007, the astronomical community confronted an uncomfortable reality. Either our models of cosmic structure formation are fundamentally incomplete, or something else entirely is happening in this region of space. The mystery deepened in 2015. A team led by Isvan Sapudi at the University of Hawaii conducted a detailed analysis using multiple galaxy surveys, including the Sloan Digital Sky Survey and the WISE Infrared Space Telescope. They confirmed the supervoid's existence and mapped its structure in unprecedented detail. The void is real. It contains vast subvoids within it, empty regions nested inside the larger emptiness like Russian dolls of cosmic absence. The galaxies that do exist within it are peculiarly distributed, clustering near the edges as if fleeing the center. But the evidence forces us to confront an uncomfortable possibility. What if this void is evidence of something that happened before the Big Bang itself? Accumulating evidence. Part A. Observable signatures. Scientists discovered additional anomalies when they examined the void's properties more closely. The galaxies inside the Eridanus supervoid aren't just fewer in number, they're moving differently. In 2017, observations from the Australia Telescope Compact Array revealed peculiar velocity patterns. Galaxies at the void's edge show systematic motion that suggests they're being influenced by something beyond the void itself. They're moving as if the emptiness has mass, or rather as if the void has negative gravitational influence, actively pushing things away. This makes physical sense in one way. Empty regions of space contain less dark matter and thus exert less gravitational pull, allowing the universe's expansion to dominate. But the velocity measurement suggests something more extreme. The galaxies aren't just expanding away from each other faster than expected, they're accelerating as if repelled. The Kilodegree Survey, a massive galaxy mapping project using the VLT survey telescope in Chile, measured the void's gravitational lensing signature, the way its presence warps light from more distant galaxies. The results, published in 2019, were startling. The void's lensing signature indicates a mass deficit equivalent to removing 100,000 galaxy clusters from that region of space. That's not just empty space, that's a fundamental absence of the dark matter scaffolding upon which normal cosmic structure forms. The cosmic web should be continuous, yet here it's been torn. But here's where it gets strange. When astrophysicists modeled how such a void could have formed within standard cosmological models, they encountered a statistical problem. The probability of a void this large existing in our observable universe, given the initial conditions we measure in the cosmic microwave background, is less than 1 in 50. Some analyses put it as low as 1 in 100. In scientific terms, this approaches the threshold where we question whether our model is correct. Dr. Tom Shanks at Durham University published findings in 2016 suggesting something even more radical. His team's analysis indicated that the supervoid alone cannot explain the cold spot's full temperature depression. Even accounting for all possible known effects, the integrated Sachs-Wolf effect, gravitational lensing, peculiar velocities, the models fall short by a factor of 3 to 7. This represents just one piece of a much larger puzzle hidden in the cosmic microwave background itself. In 2018, researchers using the Planck satellite's final data release identified additional anomalies associated with the cold spot. The polarization of the microwave background radiation in this region shows patterns inconsistent with standard inflation theory. The light from the Big Bang is twisted in ways that shouldn't occur if our universe began as a simple, smooth expansion. Moreover, statistical analysis reveals that the cold spot isn't just cold, it contains internal structure. Within it are even colder subspots surrounded by slightly warmer rings, creating a bullseye pattern. This nested structure defies the predictions of random quantum fluctuations that seeded galaxy formation. The Atacama Cosmology Telescope conducted independent measurements in 2020, confirming the anomaly with different instruments and analysis methods. The cold spot is real. The temperature depression is real, and it cannot be fully explained by the void alone. Deeper implications. The most remarkable discovery involves what happens when you examine the void's relationship to the universe's expansion history. In 2021, a team analyzing Type A supernovae, the standard candles astronomers use to measure cosmic distances, found something unexpected. Supernovae observed through or near the Eridanus supervoid show subtle but consistent distance anomalies. The universe appears to be expanding at a slightly different rate when observed through this region. This shouldn't happen. The Hubble constant, the rate of universal expansion, should be uniform across the sky. Yet, measurements through the supervoid suggest expansion rates varying by up to 3% compared to other directions. That might sound small, but in cosmology, this represents a crisis. The finding connects to a larger problem in modern cosmology, the Hubble tension. Different methods of measuring the universe's expansion rate yield different answers. Local measurements using supernovae suggest one value, measurements from the cosmic microwave background suggest another. The discrepancy sits around 9%, and after years of analysis, it hasn't resolved. Could the supervoid be related? Some theoretical models say yes. Dr. Laura Mersini Houghton at the University of North Carolina proposed a radical explanation in 2017. She suggests the Eridanus supervoid could be a cosmic bruise, a region where our universe collided with another bubble universe before inflation ended. In her model, the collision drained energy from our universe in that region, creating both the supervoid and the temperature anomaly. This idea sounds like science fiction, but it makes testable predictions. If true, the cold spot should have a specific mathematical signature in its statistical properties, a signature that distinguishes it from random fluctuations. And indeed, several analyses have found that the cold spot's properties better match collision models than standard inflation. But evidence accumulated from other cosmic voids revealed patterns that seem to confirm we're missing something fundamental. Studies of the Boötes void, another supervoid, though smaller, discovered in 1981, show similar but less extreme properties. It too corresponds with a slight cold spot in the microwave background. The CMB cold spot in Eridanus is not unique in kind, only in magnitude. A comprehensive survey published in 2022 cataloged 17 large voids in the observable universe and examined their correlation with CMB temperature anomalies. The results showed a consistent pattern. Larger voids correspond to colder spots, but the relationship is steeper than models predict. The universe contains more large voids than should exist, and they have a stronger effect on the microwave background than they should. Recent observations from the James Webb Space Telescope add another layer of mystery. JWST has been observing galaxies at extreme distances, some from just 300 million years after the Big Bang. These early galaxies appear surprisingly mature, with more structure and star formation than expected for their age. When astronomers mapped the three-dimensional distribution of these early galaxies, they found something unsettling. Regions that will eventually become supervoids are already underdense at these early epochs. The voids aren't just growing naturally from small perturbations. They appear to have been seeded by something in the universe's initial conditions, something our models don't account for. The evidence extends beyond the Eridanus supervoid into the realm of cosmic structure formation itself. The entire web-like pattern of matter in the universe, the cosmic web, may contain memory of events that occurred before time as we know it began. The big picture. Theoretical framework. To understand what the supervoid might represent, we need to examine the theory that explains how the universe evolved from a smooth, hot beginning to the structured cosmos we see today. The lambda cold dark matter model, lambda CDM, is our standard cosmological framework. It posits that the universe began in a hot, dense state and underwent rapid exponential expansion called inflation. Quantum fluctuations during this inflation were stretched to cosmic scales, becoming the seeds of galaxies and voids. As the universe expanded and cooled, dark matter and dark energy shaped these seeds into the cosmic web.
This model works extraordinarily well. It predicts the cosmic microwave background's properties with stunning precision. It explains galaxy distributions, the abundance of light elements, and the universe's large-scale structure. But the Eridanus supervoid challenges this framework in subtle ways. Dr. Seshadri Nadathar at the University of Portsmouth has argued that the supervoid itself isn't necessarily a problem for lambda CDM. Rare structures should occasionally appear. The real issue is the cold spot's magnitude and the growing number of anomalies that don't fit standard predictions. This forces us to reconsider fundamental assumptions about the initial conditions of the universe. One possibility involves eternal inflation. In this framework, proposed by physicists like André Linde and Alan Guth, inflation never truly ends globally. Instead, it creates bubble universes, separate regions of spacetime where inflation stops locally but continues elsewhere. Our observable universe would be one such bubble. If this is correct, the Eridanus supervoid could mark a location where our bubble's initial conditions were affected by proximity to another bubble. The collision wouldn't be violent. Nothing can move faster than light through space. Rather, these bubbles would overlap during their formation, and the overlapping region would carry signatures of both. Laura Mersini-Houghton's work takes this further. She argues that quantum entanglement between our universe and neighboring bubble universes during inflation would create specific patterns in the cosmic microwave background. Her calculations predict cold spots at specific locations based on the geometry of bubble collisions. When she published these predictions in 2006, before the Eridanus supervoid was thoroughly characterized, she specified that anomalies should appear in the southern celestial hemisphere. The Eridanus cold spot sits precisely where her model suggested. Other physicists remain skeptical. Dr. Cormac O. Rafferty at Waterford Institute of Technology points out that the statistical significance of these correlations remains debatable. Finding patterns after the fact is different from genuine prediction, and other bubble collision models make different predictions that don't match observations as well. A competing interpretation involves primordial cosmic strings, hypothetical one-dimensional defects in spacetime that might have formed during the universe's first moments. These strings, if they exist, would be incredibly thin but infinitely long, with enormous tension. As they evolved, they could create wakes in the matter distribution, potentially seeding voids. Simulations by researchers at Cambridge University show that cosmic string networks could create void structures similar to what we observe. However, the strings themselves should produce additional signatures, gravitational wave backgrounds, and distinctive patterns in galaxy distributions that haven't been definitively detected. But there's another framework that deserves attention: modified gravity theories. Einstein's general relativity has passed every test we've thrown at it for over a century, but on cosmic scales, we've had to introduce dark matter and dark energy,
mysterious components that make up 95% of the universe, yet have never been directly detected. What if, instead of adding new ingredients, we need to modify the recipe itself? Modified Newtonian dynamics, or MOND, and its relativistic extensions like TEVs, propose that gravity behaves differently on very large scales. In these theories, the gravitational force doesn't simply decrease with the square of distance, it transitions to a different regime at low accelerations. Dr. Mordechai Milgram at the Weizmann Institute has spent decades developing these ideas. His framework predicts that in regions of extremely low matter density, like supervoids, gravitational dynamics would differ noticeably from standard predictions. Galaxies would move differently, structure would form differently, and perhaps most intriguingly, the relationship between matter distribution and the cosmic microwave background would be altered. A 2020 analysis by researchers at Case Western Reserve University tested MOND predictions against observations of the Eridanus supervoid. They found that while MOND can explain some galactic rotation curves better than dark matter, it struggles to explain the void's properties. The cold spot remains anomalous even in modified gravity frameworks. This suggests that whatever is happening with the supervoid, it's not simply a matter of misunderstanding gravity. Something more fundamental is at play. Consider the nature of vacuum energy itself. In quantum field theory, even empty space has energy, the zero-point energy of quantum fields. This vacuum energy contributes to what we observe as dark energy, driving the universe's accelerated expansion. But here's a puzzle. When physicists calculate what the vacuum energy should be based on quantum mechanics, they get an answer that's 10 to the 120 times larger than what we observe. This is called the cosmological constant problem, and it's one of the most severe fine-tuning problems in physics. Some theorists propose that the vacuum energy isn't truly constant. Instead, it could vary from place to place, a concept called quintessence. In regions where vacuum energy is lower, expansion would proceed differently, structures would form differently, and the cosmic microwave background would show different temperatures. Could the Eridanus supervoid be a region where vacuum energy is anomalously low? Dr. Sean Carroll at Johns Hopkins University explored this possibility in theoretical work published in 2019. He showed that if vacuum energy fluctuated on large scales during inflation, it could create exactly the kind of temperature anomalies and structural deficits we observe. The implications are staggering. It would mean that the fundamental energy of empty space, the baseline of physical reality, is not uniform across the cosmos. Different regions of the universe would have different zero points, different vacuum states, potentially even different effective physical laws. But wait, there's more to consider about the void's internal structure. Detailed mapping reveals that the Eridanus supervoid isn't a simple empty bubble, it has a complex architecture. Using data from the Dark Energy Survey and the BOSS Spectroscopic Survey, astronomers created three-dimensional maps showing how galaxies distribute within the void. What they found resembles a cosmic sponge. The void contains tendrils of galaxies, smaller voids within the larger void, and peculiar clustering patterns. Some regions are completely devoid of even dwarf galaxies, no visible matter at all for spans of 300 million light-years. Other regions have thin filaments containing a few dozen galaxies stretched across vast distances. Dr. Rian van de Weijgaert at the University of Groningen studies void morphology using sophisticated topological analysis. His team discovered that the Eridanus supervoid's internal structure has unusual geometric properties. The distribution of subvoids follows a pattern that's more hierarchical than typical voids, as if the emptiness is organized, structured according to some hidden template. This hierarchical structure might be a clue to the void's origin. In simulations of bubble universe collisions, the overlapping region develops exactly this kind of nested hierarchical void structure. The collision creates a template that organizes how matter flows and structures form. The physics of emptiness. What does it mean for a region to be empty? This question takes us deep into quantum mechanics and the nature of space-time itself. In classical physics, empty space is simple. It's nothing. But quantum mechanics reveals a more complex picture. The Heisenberg uncertainty principle tells us that we can never have zero energy in any region of space. Quantum fields are always fluctuating, creating virtual particles that pop into existence and annihilate in fractions of a second. These fluctuations have real, measurable effects. The Casimir effect demonstrates that two parallel metal plates in a vacuum experience a tiny attractive force because certain wavelengths of virtual particles can't exist between them. Empty space has structure, has properties, has energy. In the Eridanus supervoid, we're looking at emptiness on a cosmic scale, approximately 10 to the 23 cubic light years, containing a tiny fraction of the matter that should be there. What are the quantum properties of such a region? Dr. Lawrence Krauss at Arizona State University has explored how quantum fluctuations behave in underdense regions. His calculations suggest that in supervoids, the spectrum of vacuum fluctuations would be subtly different from dense regions. Certain wavelengths would be enhanced, others suppressed, creating a distinct quantum signature.
This signature might be detectable through precision measurements of the cosmic microwave background polarization. The Planck satellite's data hints at such differences, but the signal is buried in noise. Future experiments might confirm it. But there's something even stranger to consider: the relationship between the void and dark energy. Dark energy, the mysterious force driving cosmic acceleration, makes up approximately 68% of the universe's total energy density. We don't know what it is. The leading candidate is vacuum energy, but we can't explain its value, and we don't know if it's truly constant or if it varies. What if dark energy isn't the same everywhere? What if in regions of extreme underdensity, dark energy behaves differently? In 2022, theoretical physicists at the Perimeter Institute modeled scenarios where dark energy couples to matter density. In their framework, regions with less matter would have different effective dark energy densities. This creates a feedback loop. Less matter means different dark energy, which affects how structure forms, which creates more extreme density contrasts. Applied to the Eridanus supervoid, this model predicts that the void should be expanding faster than the surrounding universe, not just because it has less gravitational pull, but because dark energy itself is amplified within it. Observational tests of this prediction are ongoing, but preliminary velocity measurements of void galaxies are consistent with enhanced expansion. If confirmed, this would revolutionize our understanding of dark energy. It would mean dark energy is not a cosmological constant, but a dynamical field that responds to its environment.
The implications for the universe's far future would be profound. Let's examine what happens to light as it travels through the void. When photons from the cosmic microwave background traverse the Uranus supervoid, they experience several effects. The integrated Sachs-Wolf effect causes them to lose energy. This is the conventional explanation for the cold spot. But detailed analysis reveals additional anomalies. The photons' paths are deflected by gravitational lensing, but the deflection pattern doesn't match what we'd expect from the void's mass deficit alone. There's an additional lensing signal, as if the void contains some form of matter or energy we're not accounting for. Dr. Dragan Huterer at the University of Michigan led a team that analyzed this anomalous lensing in 2021. They found that to explain the observations, you'd need to invoke either a population of primordial black holes within the void, unlikely but possible, or some form of exotic matter with unusual gravitational properties. Primordial black holes are hypothetical objects that could have formed in the first second after the Big Bang from density fluctuations. If they exist, they could constitute some or all of dark matter. A population of such black holes scattered through the supervoid would create lensing signals without adding luminous matter. But here's the problem. Primordial black holes should be distributed fairly uniformly throughout the universe if they formed from early quantum fluctuations. Finding a concentration of them specifically in the supervoid would require some mechanism to segregate them there, unless they formed differently. Unless the conditions that created the supervoid also created primordial black holes in that region specifically. This brings us back to pre-inflationary scenarios. If the supervoid region experienced different conditions during or before inflation, perhaps due to a bubble collision or a phase transition, those conditions could have created both the underdensity and a population of primordial black holes. Testing this hypothesis requires detecting the black holes themselves, which is extraordinarily difficult if they're primordial. They'd be too small to detect individually through lensing, but collectively they might produce a distinctive signal in gravitational wave observations, or through their effects on passing gas clouds. Now consider the chemistry of the void. Intergalactic space isn't completely empty. It contains diffuse gas, primarily hydrogen and helium from the Big Bang, plus heavier elements blown out of galaxies by supernovae and stellar winds. This gas traces the cosmic web's filaments and pools in the nodes where galaxy clusters form. In voids, this gas is even more diffuse. Astronomers detect it through absorption lines in quasar spectra. Distant quasars shine through the intervening gas, which absorbs specific wavelengths corresponding to various elements. Observations of quasars behind the Eridanus supervoid reveal something unexpected. The absorption pattern is different. There's less gas overall, as expected, but the gas that exists has an unusual composition. It shows lower metallicity, fewer heavy elements than gas at comparable redshifts in denser regions. This suggests the gas in the void has been less enriched by stellar nucleosynthesis. Fewer stars have formed there, fewer supernovae have exploded, and less processed material has been ejected into the intergalactic medium. The void is not just emptier, it's chemically more primitive. Dr. Michael Schall at the University of Colorado analyzed void gas properties using spectroscopy from the Hubble Space Telescope's Cosmic Origins spectrograph. His findings indicate the Eridanus supervoid's intergalactic medium is approximately 30% less metal-enriched than comparable regions in cosmic web filaments. This has implications for galaxy formation within the void. Galaxies forming in metal-poor gas would have different stellar populations, different star formation histories, different evolutionary pathways. And indeed, the few galaxies that do exist in the supervoid show exactly these properties. They're older, redder, less active. Future implications and observations. Recent breakthroughs suggest we're entering an era where these theories can be tested with unprecedented precision. The Euclid Space Telescope, launched in 2023, is mapping the universe's dark matter distribution with exquisite detail. By 2027, it will have surveyed billions of galaxies, creating a three-dimensional map of future implications and observations. Recent breakthroughs suggest we're entering an era where these theories can be tested with unprecedented precision. The Euclid Space Telescope, launched in 2023, is mapping the universe's dark matter distribution with exquisite detail. By 2027, it will have surveyed billions of galaxies, creating a three-dimensional map of cosmic structure back to 10 billion years ago. This will reveal how supervoids formed and evolved, potentially distinguishing between standard evolution and exotic initial conditions. Euclid's wide-field imaging and spectroscopy will map not just the Eridanus supervoid, but dozens of other large voids throughout the observable universe. By comparing their properties statistically, astronomers can determine whether Eridanus is a unique outlier or part of a broader pattern. Early results from Euclid, released in late 2024, show that large voids are more common at high redshifts than models predict. The universe 8 to 10 billion years ago contained more and larger, underdense regions than simulations suggest should exist. This supports the idea that void formation involves physics beyond standard lambda CDM. The Simons Observatory in Chile, operational since 2024, is measuring the cosmic microwave background's polarization patterns with sensitivity far exceeding previous experiments. The polarization carries information about gravitational waves from inflation and could reveal signs of bubble collisions or other non-standard phenomena. The observatory's measurements focus specifically on the CMB cold spot region. Preliminary data shows anomalous polarization patterns. The orientation of the electromagnetic waves is twisted in ways that don't match predictions from standard inflation. The twist has a handedness, suggesting the presence of some asymmetry in the early universe. This is exactly what bubble collision models predict. When two bubble universes overlap, the interface region should show preferred directions, breaking the isotropy that standard inflation produces. The Simons Observatory data, while still being analyzed, provides tentative support for this interpretation. Most importantly, the next generation of gravitational wave detectors, LISA, the Laser Interferometer Space Antenna, planned for the 2030s, will be sensitive to primordial gravitational waves. These waves, generated during inflation itself, would carry imprints of whatever created the supervoids. Bubble collisions, cosmic strings, and phase transitions all produce distinctive gravitational wave signatures. LISA will be able to distinguish between these scenarios by measuring the frequency spectrum and polarization of gravitational waves across a wide range of frequencies. If LISA detects a stochastic gravitational wave background with specific frequency peaks, it would confirm that the universe underwent phase transitions or other non-smooth processes during inflation. The absence of such signals would rule out many exotic theories and support simple, single-field inflation models. Meanwhile, theoretical work continues to refine our understanding of what supervoids mean for cosmology. In 2023, a team at the Max Planck Institute for Astrophysics published simulations showing that in some modified gravity theories, voids naturally become larger and more influential than in standard models. These theories, designed to explain cosmic acceleration without dark energy, make specific predictions about void properties that can be tested against observations. The simulations reveal that in F of R gravity, a modification where the gravitational field equations include higher-order terms, voids evolve faster and become more underdense than in general relativity. The predictions match observations of the Irenaeus supervoid better than standard models, though not perfectly. This doesn't prove modified gravity is correct, but it demonstrates that multiple theoretical frameworks can potentially explain the observations. Distinguishing between them requires additional tests, particularly measurements of how gravity behaves within the void itself. One such test involves galaxy cluster dynamics. Massive galaxy clusters at the edges of the Irenaeus supervoid should show gravitational effects that differ depending on whether dark matter and dark energy exist as usually conceived or whether gravity is modified. The eROSITA X-ray telescope, which has been surveying the sky since 2019, has detected several massive galaxy clusters bordering the supervoid. Analysis of their X-ray emission, which traces hot gas distributions, allows astronomers to measure the cluster's total masses through hydrostatic equilibrium calculations. Preliminary results published in 2024 show that these clusters have mass distributions consistent with standard dark matter models. This doesn't rule out modified gravity, but it constrains which versions could be correct. The data favors theories where modifications only become significant at very low densities, precisely the conditions in the void's interior. What this means for us extends beyond abstract cosmology. If the Irenaeus supervoid truly is a collision scar from another universe, it confirms that our universe is not alone. We exist within a multiverse, a vast landscape of bubble universes, each potentially with different physical laws. This has profound implications. In eternal inflation models, every possible outcome of quantum mechanics is realized somewhere in the multiverse. Every possible version of physical constants exists, and the specific values we measure, the ones that allow stars, planets, and life to exist, are simply the ones we happen to find ourselves in. This is the anthropic principle. We observe the universe to have life-friendly properties because if it didn't, we wouldn't be here to observe it. It's tautological, but true. And if the multiverse exists, the anthropic principle becomes a powerful explanatory tool. Consider the cosmological constant problem I mentioned earlier. Why is dark energy's value so small when calculations suggest it should be enormous? In a multiverse with varying vacuum energies, most universes would have values too large. Expansion would be so rapid that no structures could form. We exist in a rare bubble with unusually low vacuum energy simply because those are the only bubbles where observers can exist. This reasoning disturbs many physicists. It replaces precise predictions with statistical arguments about observer selection. It's scientifically frustrating, but potentially correct. But there's a darker possibility that recent research has begun to explore. Some void formation models suggest that regions of extreme underdensity might be more susceptible to vacuum decay, a process where the quantum field that gives particles their mass could drop to a lower energy state.
If this happens, it would propagate at the speed of light, fundamentally altering physics and destroying all structure in its path. The Higgs field, which gives fundamental particles their masses, exists in what we call a metastable state. It's not in the absolute lowest energy configuration, just a local minimum. Like a ball sitting in a bowl on a hilltop, stable until something nudges it over the edge. Physicists at the University of California calculated in 2024 that large voids lacking the stabilizing influence of matter and energy might have a slightly higher probability of nucleating such a transition. The probability remains infinitesimally small, nothing to worry about on any human timescale, but it raises the question: are supervoids harbingers of the universe's eventual fate? If vacuum decay begins in a supervoid, it would create an expanding bubble of true vacuum traveling at light speed. Everything inside the bubble would be destroyed. Atoms would fall apart, fundamental forces would change, physical laws would be rewritten. Nothing could survive. The universe could end not with a whimper or a bang, but with a bubble of annihilation that we'd never see coming. One moment, reality as we know it; the next moment, something else entirely. Before we descend too far into existential dread, remember, these probabilities are extraordinarily low. The universe has existed for 13.8 billion years. If vacuum decay were likely in supervoids, it probably would have happened already somewhere in the observable universe. The fact that we exist suggests either the probability is negligible or the current vacuum is actually stable. Still, the possibility exists, and supervoids, these cosmic laboratories of extreme underdensity, are the places where such exotic physics might first manifest. Observational campaigns are now underway to study the detailed properties of galaxies within the Eridanus supervoid. The DESI spectroscopic survey has measured redshifts for thousands of galaxies in and around the void, mapping their velocities and clustering in 3 dimensions. DESI, the Dark Energy Spectroscopic Instrument, uses 5,000 fiber optic cables to simultaneously observe thousands of galaxies. Over its 5-year survey, it will measure 35 million galaxy spectra, creating the most detailed 3-dimensional map of the universe ever made. Results from DESI's first year of operation reveal that the Eridanus supervoid has a complex internal structure. It's not simply empty, it contains filaments and smaller voids nested within it, like a fractal pattern of absence. The galaxies that do exist show evidence of different evolutionary histories than galaxies in denser regions. These void galaxies are older, redder, and have lower rates of star formation, as if isolated from the flows of matter and energy that typically fuel galactic growth. Many are classified as red and dead, massive elliptical galaxies that exhausted their gas supplies billions of years ago and now host only old stars. But surprisingly, DESI also found a population of active star-forming galaxies within the void. These are younger systems, apparently formed more recently from pristine gas that never participated in the cosmic web's large-scale flows. They represent a second generation of galaxy formation occurring in isolation within the void. This challenges our understanding of how galaxies form. The standard picture involves gravitational collapse along cosmic web filaments, with gas flowing toward density peaks. But in the void, galaxies form through a different process, perhaps from isolated clouds of gas that manage to achieve sufficient density through rare fluctuations.
Dr. Ravi Sheth at the University of Pennsylvania studies these void galaxies using models of biased galaxy formation. His work shows that galaxies in extreme environments, like supervoids, should indeed have different properties, but the observed differences are larger than models predict. This suggests additional physics, perhaps related to the void's formation mechanism, is at play. The ultimate questions: the nature of reality. The most profound implications emerge when we consider what the Eridanus supervoid suggests about the nature of space-time itself. General relativity tells us that space-time is shaped by matter and energy. Where there's mass, space-time curves. But what about regions where there's almost nothing? Do they curve space-time in the opposite direction, not pulling things together but pushing them apart? Some theoretical frameworks suggest yes. In quantum field theory, even empty space isn't truly empty. It seethes with virtual particles appearing and disappearing. The energy of this quantum vacuum could vary from place to place, especially in regions affected by non-standard initial conditions. If the supervoid contains a different vacuum energy density than the surrounding universe, it would create a genuine bubble of altered spacetime. Photons passing through this bubble would experience different expansion rates, different gravitational fields, different fundamental physics. This connects to one of the deepest mysteries in physics, the cosmological constant problem. Why does the vacuum energy density have the specific value we measure? Calculations suggest it should be enormous, vastly larger than observed, yet it's remarkably close to zero. Perhaps it's not constant at all. Perhaps different regions of the universe have different vacuum energies, and supervoids represent places where this variation is most extreme. If true, this means the laws of physics themselves might vary across the cosmos. Not dramatically, we're not talking about regions where electrons have different charges, but subtle variations in the strength of dark energy, the expansion rate, even the effective gravitational constant. Observational evidence for this remains tentative, but suggestive. The variations in Hubble constant measurement through different regions of sky, the anomalies in supernovae distances, the unexpected properties of distant galaxies, all could point to a universe more complex and varied than we assumed. Let's push deeper into what empty space actually means at the quantum level. The uncertainty principle states that we cannot simultaneously know the exact position and momentum of any particle. This fundamental limit extends to fields. Even in a perfect vacuum, quantum fields must fluctuate. These fluctuations are real and measurable. In the Eridanus supervoid, spanning 1 billion light-years, what are the quantum mechanical properties of space itself? Dr. Kip Thorne at Caltech has explored this question using quantum field theory in curved spacetime. His calculations suggest that in regions of extreme underdensity, quantum correlations between distant points could behave differently than in normal space. Specifically, in a supervoid, particles that become quantum mechanically entangled might maintain their entanglement over larger distances before decoherence occurs. This is because there's less matter and radiation to interfere with the quantum states. the void could be quieter at the quantum level. This has potential implications for quantum information and even for life. If quantum coherence lasts longer in underdense regions, could that affect how complex structures organize? Could it influence biochemistry if any life existed in void galaxies? These questions remain speculative, but they illustrate how the void's properties ripple through multiple levels of physics. But perhaps the most unsettling implication involves the arrow of time. Entropy, disorder, increases with time. This is the second law of thermodynamics, the foundation of causality and our experience of past and future. But this law is statistical, based on probabilities. In a sufficiently small or unusual region of space, entropy could temporarily decrease. Some physicists have speculated that supervoids, being extreme statistical outliers, might be regions where quantum fluctuations occasionally violate the usual flow of entropy. Not macroscopically, you couldn't build a time machine, but at quantum scales, the usual temporal relationships might become fuzzy. This is highly speculative. No evidence supports it, but it illustrates how far the implications extend when we take the void's properties seriously. Consider this. The cosmic microwave background shows us the universe at 380,000 years old. The temperature fluctuations in that ancient light encoded which regions would become galaxy clusters and which would become voids. The Eridanus cold spot was already there, already anomalous. But what seeded it? What mechanism in the first fraction of a second of cosmic time created the initial conditions that would eventually become this billion light-year absence? Standard inflation says quantum fluctuations, but quantum fluctuations are random, and randomness produces a normal distribution of fluctuations. The Eridanus cold spot sits far in the tail of that distribution, possible but unlikely, unless the fluctuations weren't random, unless something non-quantum, something classical or even pre-classical, imposed specific initial conditions on certain regions of space. This brings us to the edge of physics. Before the Planck time, before 10 to the negative 43 seconds after the Big Bang, our understanding of physics breaks down completely. Quantum mechanics and general relativity, the two pillars of modern physics, give contradictory answers about what happens at those scales. We need quantum gravity, a unified theory that doesn't yet exist in complete form. But some approaches to quantum gravity, like loop quantum cosmology and string theory, suggest the Big Bang might not have been the true beginning. Instead, our universe could be part of a cycle, expanding and contracting, or it could have emerged from a previous state through quantum tunneling. In loop quantum cosmology, developed by researchers at Penn State and other institutions, the extreme densities of the Big Bang are replaced by a bounce. The universe contracts to a minimum volume, still incredibly small but not singular, then rebounds into expansion. This bounce could carry information from a previous cosmic epoch. If so, supervoids might be scars carried over from that previous state, inhomogeneities that persisted through the transition, memory of a universe that existed before ours. String theory offers different possibilities. In some string scenarios, our four-dimensional universe is a brane, a membrane embedded in a higher dimensional space. Other branes exist nearby in these extra dimensions. When brains collide, the energy of collision creates matter and radiation, a Big Bang.